Okay, good morning. So till now we have covered 7 lectures. In the last lecture, we talked about limit of a function, right? And that is from the point of view of epsilon delta. So I hope you remember the definition. For every epsilon positive, there exists delta positive such that what happens? Mod of f of x minus L is less than epsilon. Whenever 0 is less than mod of x minus a is less than delta, right? And I think as I can see, some of you are discussing about various things on, I mean, I think you are reading some Thomas calculus, some examples, right? Which is good thing. So now we are going one step further. And so we started with, so if f of x, so y is equal to f of x is a function. So of course you can make a graph of it, right? I mean, a function can be represented by a graph, right? In x-axis, y-axis, they can plot the graph, right, of the function. By the way, how will you plot x raised to power x? T time problem, right, from the beginning. How will you plot x raised to power x? I mean, okay, just try to plot. Anyway, so this is just a, warm-up exercise from your JEE thing, right? Anyway, so now we have this function. So loosely speaking, say that if when you draw the graph of a function, if there is no break at any point, right? So we say that it is a continuous function, right? Or we call it satat falan, right? In Hindi, if you remember, satat falan, continuous function, right? So we can actually give the definition in terms of limit of a function also, right? So we can use this definition. So basically, I want to check whether the function is continuous at a particular point A, right? So basically what I need to do, I should take the limit of the function f of x as x tends towards A. And if it turns out to be the value of f of a, that means there is no break, right? If the value turns out to be exactly, the value of the function. Okay, so that way we can determine if the function is continuous or not at a given point, right? And if you want to check for the whole domain, you can just vary the point, right? And you can check it for all the points on the domain. So two concepts are important. One is continuity of a function. Function should be continuous. So what is the definition? So limit of the function. So limit should exist, number one. Function should be defined at that point. And third, limit should equal to that value of the function, right? These three, this is, I think you know from your JEE exam, right? And but you know that we don't like this definition. We want epsilon delta business, which I'll write it, right? I'll talk about that definition. Second thing, another important thing is uniform continuity. So many times what happens, continuity of a function, okay, is independent of points. So basically if I take 2 points and I can, the function, is uniformly continuous. So basically, I'll show you in the epsilon delta definition. So delta normally depends on epsilon and the point A under consideration, okay, when we talk about continuity of a function. But if it is independent of the point A under consideration, I will show you with examples so you will understand. So then we say that the function is uniformly continuous. So many times what happens in one domain, if you take the function, it may not be uniformly continuous, but if you change the domain, it may become a uniformly continuous. It all depends what points you are considering, right? So these are the two important concepts which I am going to talk about: continuity of a function, right, and uniform continuity. These two concepts, and I am going to only do epsilon delta examples so that you really understand, okay? And what are the background for you to understand these things? Mathematical maturity in terms of, how do you play with the inequalities? That's all, okay? Because when we deal with these epsilon delta definitions, we look at mod, this and that, and use those things. So that is the only thing to worry about. So let me start with continuous function. So so this was the definition of limit of a function, right? I think you remember. For every epsilon positive, there is delta positive such that whenever 0 is less than mod of x minus L is less than delta, mod of f of x minus L is less than epsilon, right? And they remember this 0 point is required because, many times the function may not be defined at a, right? So for example, sin x by x is a well-known example. Okay, anyway. So this is all about limit. Now we talk about, so I can actually give you analogy, and this is kind of useful. Between limit of a sequence first and limit of a function. So you can clearly see what happens. So we have a sequence. Okay. And here we have f is a function. So y is equal to f of x is a function, right? So here domain is natural numbers, right? And here domain is real line, or subset of real line, that is okay. Here the notation is Sn, here, and here the notation is f of x. Point is same. Here we talk about when the n approaches towards infinity. Here x approaches towards point A, right? Epsilon here, that concept is same. Here, we have a number n, right? For all n greater than or equal to capital N, things should happen. Here we have delta, okay? So here we write condition that n is greater than or equal to capital N, means for sufficiently large n. We sometimes read it like this: for sufficiently large n. Okay? So n is sufficiently close to infinity, but it is not equal to infinity, right? And here we have this condition: 0 is mod of x minus a is less than delta. So x is close to a, but not equal to a. Okay? This is a very nice analogy. You can see limit of a sequence, limit of a function, right? So what do you need to replace? Many times people are confused even in this also. That's why I have written this analogy, right? A sequence Sn converges towards L if for every epsilon positive, there exists a number capital N integer such that mod of Sn minus L is less than epsilon for every small n greater than or equal to capital N, right? That's the definition you can form. And there, limit of a function at a point x equal to a is that limit of a function f of x is L, capital L, if for every epsilon positive, there exists delta positive such that mod of f of x minus L is less than epsilon, right? Whenever 0 is less than mod of x minus a is less than delta. Got it? This nice comparison should be clear in your mind so that there is no confusion. When you're dealing with sequence of a sequence, definition is a little bit different. When you're dealing with function, okay, definition is a little bit different, right? Because in case of sequence, we are only talking about the convergence of a sequence. So we just want to check whether the limit exists as n approaches towards infinity. And here x approaches towards a point A, right? So this is the key difference. So I think rest of things are almost, so you can form a definition very easily, right? Okay. Now we can give you the definition of continuous function. So we say that function f is continuous. These are all shorthands I use CONT double dot S, continuous. The mathematician always like writing shorthand. Why to write so much language, right? So function is continuous at point A. At a point A on the real line if three conditions should be satisfied. Number one, limit of f of x as x tends towards A exists. First condition. Second, the value of the function should be defined at A. right? And third, this limit as x tends towards a should be equal to the value of the function. This is a very, very nice definition, and you know about it, right? And obviously, if this happens, you will see that there will be no break, right? When you draw the graph, right? So this is the definition of continuous function. And obviously, when you do this, since we have this thing here, right? This condition of limit, and I have epsilon delta business. So I can easily write down the formal epsilon delta definition of a limit. And that will be that function f of x is continuous at a point x is equal to a if for every epsilon positive there exists delta positive such that mod of f of x minus, in place of L, I will have the value of the function which is f of a is less than epsilon. So this modification you need to do. Second modification in the definition, whenever it was earlier 0 is less than mod of x minus a less than delta. Now 0 will not be there because we need to define function at x equal to a, because that is the second condition. Function should be defined. So that 0 word will be dropped and you are left with mod of x minus a less than delta. This is how you can form the definition easily, right? Just modify the, because I'm using the same definition, whatever we are using here. The only thing is that now capital L is f of a, right? Okay, so we can easily form the definition, right? So let me write down the formal definition now. So we say that a function f is continuous at a point A on the real line when only if for every epsilon positive there exists delta positive such that mod of f of x minus f of a is less than epsilon whenever mod of x minus a is less than delta. You can clearly see that from the previous definition, capital L is replaced by f of a, right? Because the limit is now f of a, and here positive thing is dropped. So, x has to be defined. So now in the interval, so basically, again, if you remember in terms of neighborhood, what is happening, I can just write down that picture here. So in terms of neighborhood, what is happening? This is the point A minus delta, a plus delta, because this corresponds to what? Minus delta less than x minus a less than delta. This implies that a minus delta is less than x is less than a plus delta, right? So we are getting this neighborhood, right? Clearly? And what about this one? This you can say that minus epsilon is less than f of x minus f of a less than epsilon. You can add f of a on both sides. So basically you are getting something like this. This is f of a minus epsilon, f of a plus epsilon. So whenever x is in the neighborhood of a, this means whenever x is in the neighborhood of a, its image is in the neighborhood of f of a, right? So here somewhere, I mean, this is, I'm just writing, it could be anywhere, right? Anywhere in the neighborhood, right? And again, I am showing it, different lines, something on the same real line I'm talking about, just to show you in a much better way, right? So whenever x approaches towards a from either side, left hand or right hand, right? Yeah. So image is always in the neighborhood of f of a. If this happens, the function is continuous, right? Correct? Understood? Any question? Because many times you are finding it difficult to absorb these things, thanks to Bolzano who started these things, right? So you like Bolzano now? No. It's a beautiful concept, right? Limit of a function, first limit of a sequence, epsilon n. Limit of a function, epsilon delta, and limit and continuity. So once we are done up to continuity, we'll also talk about differentiability in the same sense. In fact, anything you can talk with epsilon delta business. It's a beautiful business, right? Okay. So these are the three concepts that you need to know: epsilon n method, epsilon delta for the limit, and epsilon delta for the continuity of a function. Okay. So I can give some examples, right? One example maybe I can just write down, and then suppose I take a function g of x equal to sin x by x when x is not equal to 0, and at origin the value is 1. So you can clearly see that g is continuous at x equal to 0. Why? Because if you take the limit of gx as x tends towards 0, this value is 1, right? g0. The function is continuous at origin. Actually, if you drop this condition of 1, okay, then the function will be discontinuous at origin. So remember, if you modify the function, there will be an issue, right? Now, as soon as I give the definition of continuity of a function, a series of t-time problems will emerge for you to enjoy. So I'm going to say that, please note it down carefully. Give an example of a function on the real line which is continuous exactly at one point. Give an example of a function which is continuous exactly at one point on the real line. Okay? Got it? So t-time problem number 1. Give an example of a function which is continuous exactly one point on the real line, nowhere else. Second t-time problem. Give an example of a function which is continuous exactly at 2 points on the real line and nowhere else. Or if you keep on doing, give an example of a function which is continuous exactly at n points on the real line. Exactly at n points on the real line and nowhere else. Right, so 1 point, 2 point, 3 point. So basically on certain number of points, the function is continuous. Otherwise, it is not continuous. So when you do this exercise and enjoying a cup of tea, you will enjoy, beauty, real beauty. You see that you will learn everything about epsilon delta when you play with these examples. Okay. So ये तो एक side था. Now the other side. Give an example of a function which is discontinuous exactly at one point on the real line. Then give an example of a function which is discontinuous exactly at 2 points on the real line, and 3 points on the real line, or n points on the real line. Got it? So on one side it is I am asking examples for continuity, other side I am asking example for discontinuity on n points on the real line. So if you do this exercise, you will really enjoy the beauty of mathematics, Then I can go one step further. Give an example of a function which is continuous at all integer points on the real line. Only on integer points it is continuous and nowhere else. See? Beautiful problems, right? So, सोचने पे मजबूर करेगा, but you will enjoy the beauty, right? Which is only, I can say that I set all integer points. Similarly, I can say that give an example of a function which is continuous at all even integers and discontinuous at all odd integers. So all kind of questions can be framed. So easy for me to generate new questions, t-time problems. That is how we design the papers, your question paper. When I am sitting there, whatever comes into my mind, I will write it down. You might have seen some of the things in your sample papers, right? Okay, so you got how many? Bunch of t-time problems, right? You want me to repeat any question or no, it's clear? Function which is continuous at certain number of points, function which is continuous at discontinuous at certain number of points, right? Function which is continuous at all integer points, function which is discontinuous only at integer points. All kind of questions can be framed. You yourself can create new questions, right? And try to solve it. Okay, so I think that's about this. Now let me show you some more beautiful things. There is a, another interesting result, which I am not going to prove it, but just I will just mention it. And the result says that a function f is continuous at a point A on the real line if and only if whenever there is a sequence xn n is equal to 1 to infinity which converges towards A, then the sequence f of xn also converges towards A. One can prove it, but even if you don't prove it, it's okay for me at the moment. But just, but this is a very useful result in proving this continuity, discontinuity. You can use it as a tool to prove certain things, right? The function is continuous. You can talk in terms of sequence, right? If there is a sequence of integers, sequence of real numbers which converges towards A, and if it happens that image also converges to the image of A, then the function is continuous. Okay, I think if you think a little bit with a cup of coffee, you will be able to see why this is happening actually, right? In terms of sequence, why things are happening, right? That is something to do with the structure of the real line. But anyway, that's something very important result, and one can use it for proving certain things. Okay, for proving certain things in the. Okay. Now I am going to talk about uniform continuity. Now I am going to give you some examples. I will show that now the continuity of a function at a point, depends on not only when we determine delta, okay, the delta depends not only on epsilon but also point A under consideration. I'll give you explicit example, okay, and if we are able to find delta which only depends on epsilon, then the function is uniform continuous, okay. So this is the thing. So let me show you the example. Take an example. So I should mention here in general. Okay, so basically, what is the definition of continuity? A function f is continuous at A on real line. I'm just writing the definition again. If for every epsilon positive or given epsilon positive, there exists delta positive such that mod of f of x minus f of A is less than epsilon whenever mod of x minus A is less than delta. So whenever x lies in the neighborhood of A, its image of basically all the images lie in the neighborhood of f of A, right? That's the definition, right? So I am saying that in general, delta depends not only on epsilon but also point A under consideration. So here is an example. You can see how this statement I'm going to show you. Take the function g of x is equal to x squared and the domain is whole real line. Function g of x is equal to x squared, domain is whole real line. So actually I'm going to show you this function is not uniformly continuous. That means delta depends not only on epsilon but also on the point A under consideration. By changing the point, you see the behavior will change. Okay, so let us see this. Observe it carefully. So if I take epsilon is equal to 2, so the statement mod of g of x minus g of A will be less than 2. Sorry. So we are taking epsilon is equal to 2, right? So definition is what? That mod of f of x minus f of a is less than epsilon, right? So epsilon is 2. I will try to find a delta, which depends on, of course, what delta is there, right? So now this is statement that mod of g of x minus g of a is less than 2 if we take mod of x minus a less than half. This is true if a is equal to 1. First of all, I want to put it in the box. This is equation 1. So what actually this bar is not there. Maybe I should write it again, right? I mean, it's creates confusion anyway. So we say that g of x minus g of a is less than 2 whenever mod of x minus a is less than half. Is true if a is equal to 1. This is equation 1. You can see that. So mod of g of x minus g of a should be less than epsilon whenever mod of x minus a is less than delta. So I'm taking actually delta is equal to half. You can see that if I take a is equal to 1, delta is equal to half, everything is valid. This inequality is valid where g of x is x square. Let me show you. Okay, everything is okay. So, because in this case, what happens? G of x minus g of a, g of x minus g of a will be what? X square minus a square. The function is f of g of x equal to x square, right? And this value will be what? Because a I am taking 1, so this is x square minus 1. Okay, fine. Now, if delta is half, if mod of x minus a is less than half, this will imply that x lies between half and 3 by 2. Right? You can determine that, right? Fine. And so this implies that minus 3 by 4 is less than g of x minus g of a less than 5 by 4. X square minus 1 will be lying between these two values, right? So everything is making sense. So basically, this definition, this statement is true if we take point A is equal to 1. If delta is half, so what I'm doing, I'm choosing epsilon to be 2, I'm choosing delta to be half, and then this whole statement works out if A is equal to 1. Right? I mean, simple calculations will show you that this is true. Now I'm going to change point A, and you see this is no longer true. Okay? Okay. So now I take A is equal to 2. So A is equal to 10. In this case, what will happen? G of x minus G of A is equal to x square minus 100. Okay. So if I take x to be 10, 1 by 4, then mod of x minus a is less than half, but g of x minus g of a is equal to 10 1 by 4 whole square minus 10 square, which is 5 1 by 16, which is greater than 2. So essentially, g of x minus g of a is greater than 2. So that inequality is no longer valid. On the gx, so gx, if the gx is defined, gx equal to x square on the whole real line, for one point A, everything is okay. For other point, it is not okay, right? The inequality is not valid, right? So that means this function is not uniformly continuous, right? So basically, I can give you a bit more. So this was just a simple example. Now let me show you. Even though G is continuous at A is equal to 10 and A is equal to 1, both point it is continuous. The number delta is equal to half is usable at A is equal to 1, but not at A is equal to 10. As a delta corresponding to epsilon is equal to 2. Epsilon is fixed here, okay? Epsilon is fixed. G is continuous both at point A is equal to 10 and at point A is equal to 1, but the same delta is not working for both the cases, you see, right? Here you see, here again I have taken delta is equal to what? This is our delta. Right? So here there is a problem. Take the same delta. So essentially, in fact, I can show you even much better result. Our claim is there is no one delta positive such that the statement g of x minus g of a is less than 2 whenever mod of x minus a is less than delta. Is true. Okay, so we don't have, there is no one delta positive such that this less than 2 whenever mod of x minus a is less than delta is 2, right? So I think थोड़ा सा ध्यान देने की बात है, if you remember, right? So g of x is equal to x square. This function I am taking 2 points. One is a is equal to 1, another one is a is equal to 10. Same delta is not usable at both the points, right? That's what I have shown you, right? So there is an issue. Okay. And in fact, there is a much more general claim. Now I can show you also this calculation. There is no one delta positive such that mod of gx minus g of a is less than 2 whenever mod of x minus a is less than delta, right? Is 2. So for every a in real line. So let me show you. So actually, I will show you that delta depends not only on epsilon but also a point under consideration. That is my point. So for g of x minus g of a is equal to x minus a into x plus a, right? Because x square minus a square, right? So our inequality is this, right? Suppose I'm again going to assume that suppose this result is true. Delta positive, I don't know why. Such that. So there is no one delta positive such that mod of gx minus ga is less than 2 whenever mod of x minus a is less than delta. So the thing is that this is true for every a. So I am going to show that suppose this is true. And then suppose there is a delta for which I can call it equation 2, I guess. Yeah. 2 holds for every a, okay, on the real line. In that case, then for suppose for a point a positive, suppose I'm taking a to be positive and x to be a plus delta by 2. Okay. Then mod of GA of X minus G of A is equal to mod of X minus A, mod of X minus A times mod of X plus A. This is what this whole thing is, delta by 2 times mod of 2A plus delta by 2, which is less than 2 by definition. We know that the whole thing is less than 2 by definition. This is given to us, right? This whole thing is less than 2, right? This whole thing is less than 2. So this whole thing is less than 2. This will simplify that A delta is less than 2 for every A positive, which is false. So that means there is no one delta. थोड़ा सा सोचने वाली बात थी, शायद तुमको थोड़ा सा हैवी पड़ा होगा, right? I know कहाँ पे डिफिकल्टी है, I know, right? तो इसलिए एक बार इसको ध्यान से पढ़ना दोबारा, ठीक है ना? I'll share the slides also, you can look at it. वैसे नोट्स में भी लिखा हुआ है, right? You can look at the notes also. So basically the point that I want to say that the function g of x is equal to x square is not uniformly continuous. So I am showing you that. So normally what happens whenever we are looking at the continuity definition, delta depends not only on epsilon but also point A under consideration. That was clear by that example, right? So now when it happens, the delta only depends on epsilon, then the function is uniformly continuous. Same function, if I close into the interval -1 and 1, it will become uniformly continuous. So this is the beauty, actually, right? Same function, if you change the domain, it becomes uniformly continuous, right? But if you take the whole real line, all kind of bizarre things happens, depending upon which point we are taking and so on, right? For some point this is happening, some point it is not happening, right? So please go over it, and if you are still having problem, you ask, okay? Yes. Because I'm taking some point. Because see, I have assumed that there is one delta for which 2 hold that previous inequality, right? So I'm saying, okay, suppose A is positive, and as I'm just trying to arrive at a contradiction kind of thing, right? So there is a false. See, whenever we are trying to do contradiction things, we have to choose just certain points for which things are not valid, right? Okay, I'm just showing that. So basically, the function g is equal to x square corresponding to epsilon is equal to 2. There is no delta that work for every A simultaneously, right? Even though G is continuous at each A on the real line. Okay. Function G is continuous on each point on the real line. That is a separate thing, but it is not uniformly continuous. So there is a difference. You need to understand what is uniformly continuous. In fact, one can also show that the function is uniformly continuous by using 2 points, say, x1 and x2. So suppose there is a function f of x, and you are able to show that mod of f of x1 minus f of x2 is less than epsilon whenever mod of x1 minus x2 is less than delta. Then also you are done. Okay, you are taking any 2 points and the similar definition works. Okay, so that is something is possible. So formal definition is a function f is uniformly continuous if it is continuous function and given epsilon positive, we can always find, or we can always choose delta, so that delta depends only on epsilon, but not on A. This is a important thing. So I guess, again, so maybe using some MATLAB or Mathematica, you can draw the same function and see the pictorial thing also, right? Draw the function on the interval and on the whole real line and see, okay, how it behaves. So you can see the some difference anyway. So now I can list down certain examples. Function f of x equal to x squared is uniformly continuous on closed interval -1 and 1. Same function is continuous when you choose closed interval -1 and 1. Right. Another example. F of x is equal to sine x, where -infinity less than x is less than infinity, whole real line, is uniformly continuous. Another example. Oh yeah, so I forgot. X is this function is discontinuous everywhere. Some examples are listed there, but okay. So this is an example of a function which is discontinuous everywhere. So I talked about function which is continuous at only one point. Here is an example of a function which is discontinuous everywhere on the real line. But all these things you have to show using epsilon delta. तो थोड़ा काम बढ़ा हुआ है. But I think there is a weekend, right? Thursday को छुट्टी भी है, right? So you can enjoy. बढ़िया का, sun is there. Take a cup of tea and play with continuity and uniform continuity. You will enjoy, right? So I know this portion was a bit tricky. So I request you to please go through over it again and try to, because see, there is another way one can talk in a loose term, but I wanted to give you some थोड़ा सा rigor भी होना चाहिए ना, तभी तो beauty आएगी ना, you will enjoy that kind of, because what happens, why we are focusing more on epsilon delta when there is an unknown problem in front of you. We are working on some problem as an engineer or something, and then you have only this epsilon delta to save you. Okay, you can think only in those terms. Okay, otherwise what happens, if it is not in the book, not in the Google, what will you do? Whom to ask? So you to ask, epsilon delta is Google for you, right? So you should you take the help of epsilon delta to look at the things, okay? So you need to do some practice actually of these epsilon delta problems. I think I have shared one link where initially a couple of examples were there. There are plenty of, I mean, there are so many solved examples you can find on the web, right, about epsilon delta business. You need to understand it clearly. Crystal clear hona chahiye definition, right? Because this is what is going to come. Okay? So now we have some time. I think I can do one more example. I define a function chi of x is equal to 1 if x is real number and x is rational, and is equal to 0 if x is real number and x is irrational. So this function is what? Continuous or discontinuous? So this function is defined for every a, right? So I mean, this function is also discontinuous everywhere on the real line. I'm going to show you through epsilon delta, okay? So what I'm going to show that this limit does not exist. Okay, and then if you see, you have to take the limit, function should be defined, and both the things should be equal. Then only the function is continuous, right? So I'll show you that limit. So I have to say that limit of chi of x as x tends towards a does not exist for any a on the reals. If this limit does not exist, the function is discontinuous at every point on the real line, right? That will be okay, right? If you are able to show this. Okay. Suppose, so contradiction, we will use the contradiction method. Suppose, so limit x tends to a, chi of x is L, exist for some real number L. So remember, I have to arrive at a contradiction. So this epsilon delta so epsilon I can choose something which will make sure that this is not valid. I choose, and you may ask again, how do we decide who is going to tell us what to take? That is by observation. When you have this habit of observing the beauty, you will realize this, right? Given epsilon is equal to 1 by 3, there would exist delta positive such that by definition mod of chi of x minus L less than 1 by 3 if 0 is less than mod of x minus a is less than delta. I have only written the definition in terms of limit, right? Limit, right? I'm just computing the limit of the function chi of x as x tends towards a. This function is pretty interesting. It says that whenever there is, if you are walking on the real line, whenever there is a rational number, you just drop one, right? And otherwise, don't drop anything. Just characterizing the rational numbers on the real line. So I want to show that this function is discontinuous at every point on the real line. So that I'm going to show that by showing that the limit does not exist for any a. So suppose limit exists and the value is L. Choose epsilon to be 1 by 3, then there will be a delta positive such that this is less than 1 by 3 if 0 is less than mod of x minus a is less than delta. By definition, now, right? Now what I'm going to do, I look at this interval a comma a delta. A comma a plus delta on the right side of the neighborhood of a, right? X approaches towards a from left side and right hand side. So in the neighborhood of a, here I am looking at from the right hand side, right? Now in this interval a plus a comma a plus delta, there will be rational numbers, there will be irrational numbers, right? Both the numbers will be there. So if x is a point between a comma a plus delta and is rational, if x is a rational between a comma a plus delta, then what will happen from here? We will get 1 minus L less than 1 by 3 because the value is 1. Chi of x will be 1 if x is rational, right? So you get this. And if x is irrational, if x is irrational, then what will happen? We will have in the neighborhood. You may say that why we are talking only in this neighborhood only. We should worry about the left hand side also. No, I have to show the contradiction. I am saying that just take some specific values, right? So I'm just focusing on one side of the interval of a, the neighborhood of a, okay? And say if x belongs to a comma a plus delta, so it has rational numbers, irrational numbers. For rational numbers, I will have the inequality mod of 1 minus L less than 1 by 3. For irrationals, I will have mod of 0 minus L less than 1 by 3 for the same x, right? So now that means what? This is not possible, right? This inequality is not possible. So there is a contradiction. Carefully designed proof, right? Okay. So the limit does not exist. So limit does not exist. The function is discontinuous at every point on the real line. Okay. Any question? Any question? Huh? No questions. So no questions means either you understand everything or you don't understand everything. It's only binary thing, right? There is no fuzzy thing. So what is the thing? It's a 1 or 0? Zero. So you could not understand anything. See, actually, there is a diversity. Each individual, the human intelligence is different. Their background is different, right? Their thought process is different. So maybe some of you will have a bright thinking, and I welcome that. And that's what I want to see in your exam also. I would like to see your beautiful mind, right? What you can do with it, right? So enjoy. I hope. I know that आज का लेक्चर थोड़ा सा भारी था बीच में, but it's okay. You will come back. Okay, you repeat it. Okay, thanks.